Thank you all for joining my thesis defense. The title of my thesis is Towards an Adaptive Optimization Framework for Urban Planning and Design. Before I begin, I would like to give a quick introduction. And since I'm a PhD candidate under the ASD pillar, my mentor is Professor Peter Ongna. The chair of the TEC is Professor Sam Joyce. The internal TEC members are Professor Ilano from ASD and Professor Song Peng from ISTD. And the external members of the TEC are Tony, for Director of DPL at URA, and also Dr. Chong, current Chief Planner at HTP. I'd like to begin with an introduction to the topic that I'm covering. Analogously, the process of urban planning and design is kind of like designing a puzzle. It involves designing many interconnected pieces, where changing the design of one would affect the whole. With so many interconnected parts, computational processes, especially things like optimization, becomes invaluable tools. Before proceeding, I would like to define some of the following key terms. Urban planning and design means the process of shaping the physical, functional, and social structure of the urban environment. Computational modeling is the use of algorithmic methods to simulate, predict, or analyze urban features. And with that, optimization is then the use of such strategies to systematically adjust the parameters of computational models to achieve the best outcomes. And finally, adaptive means it refers to the ability of a process or a framework to respond to changing conditions. Very simply, a typical design optimization framework begins by defining the parameters and the objectives that guide the use of a single model. Optimization is then introduced through this iterative loop. This approach to design exploration has gained significant traction in recent years, including within planning agencies such as URA, which brings me to the context of my PhD. My research is part of an industry collaboration between SUPD and URA, which has spanned nearly the entire duration of my doctoral journey. The project is entitled Computational Modeling for Optimization of Planning and Urban Design Parameters, and it involves 3 work packages. These 3 work packages link to the themes of computational modeling, optimization, and design space exploration. Through this industry collaboration, I had the opportunity to speak with planners early on in my PhD journey. And from these conversations, it became clear that while there's a growing interest, the adoption of optimization in practice is still quite limited. These early conversations, combined with my own preliminary research and project requirements from this collaboration, helped to define the research objectives and broader research questions. The research objectives is then to identify and address critical barriers to the adoption of optimization-based design processes in urban planning and design, and to develop a practical framework that facilitates their integration into planning and design workflows. Research question 1 that asks, how can the barriers to the adoption of optimization in urban planning and design be systematically identified? And subsequently, how can each of the barriers be addressed? Research question 2 asks, how can we prototype a modular, adaptable, and transparent optimization framework that addresses the structural and computational challenges of urban planning and design, and validate it through real-world case studies and collaboration with planning practitioners? The formulation of research question 2 was primarily guided by the requirements of the project. And while proposing a novel framework method ideal for improving the optimization, doing so without deeper understanding of each topic would be quite premature. And so we first set out to conduct a literature review to address the first part of this question 1. In this second chapter, to answer how can barriers to the adoption of optimization in urban planning and design be systematically identified, we analyzed 88 articles in a systematic literature review using the PRISMA framework. And from this literature review, I identified 7 key research categories and provided detailed discussions of each category and recommended focus areas to overcome barriers of adoption. This review draws from our published work in the Journal of Urban Science. The review of these 88 articles revealed specific gaps to be further addressed. Firstly, the first research gap is, although urban planning and design clearly involves multiple model types, few combine them in their studies with optimization. This gap is supported by point A, which shows that 57 articles studied, only 2 combine multiple model types. Similarly, Michael Betti also prominently emphasized the use of multiple models in his article published in 2021, simply called Multiple Models. Secondly, conducting multi-objective optimization typically involves many parameters and objectives, which makes the results of optimization difficult for users to understand and internalize. This gap is supported by point C and point D, where only a small number of articles propose solutions-based exploration methods to enhance the usability of the optimization process. And even fewer articles compare the optimization algorithms to improve efficiency. The third research gap is that surrogate models speed up optimization, but the lack of generalizability often leads to repeated training, making the effort redundant. This gap is supported by point E, where from the 12 articles that we studied and proposed surrogate models for wind or energy simulation, we found that each of these 12 articles used a different approach and different features for the training. And this raises concern about the reusability of the surrogate models that they proposed. These 3 gaps that I identified help to formulate more specific research questions. And these specific research questions, RQ 1.1, 1.2, and 1.3, correspond to each of the gaps identified. Chapters 3, 4, and 5 will then specifically address each of them respectively. Finally, in Chapter 6, we synthesize the insights and outcomes from all of the work presented to propose integrated optimization framework to answer research question 2. And that brings me to Chapter 3 of this presentation, where we ask that, given the inherently non-linear process and social challenges of urban planning and design, how can we structure a web tool to be iterative and user-friendly for design optimization? We developed and validated a semi-automated web-based generative planning tool that integrates back-end Rhino Python capabilities, e-planners, front-end web interface that supports iterative workflows. Part of the work that contributed to the design of the user interface in this chapter was published in a conference for modeling and simulation back in 2023. At the start of the thesis, we found that the process of urban planning and design varies significantly based on the planner's experience. In a preliminary workshop, we gave 2 groups of 3 planners the same hypothetical problem of redeveloping a site. We found that to do so involves many smaller tasks. To further complicate things, these tasks that we identified and the sequence of addressing these tasks, it varied depending on the individuals within the group. The difference in the resulting flowchart of their process highlights that there is some ambiguity in the scope and the hierarchy of tasks relating to the process of urban planning and design. We also studied and compared different web tools for urban planning and design. We chose to study web tools firstly due to project requirements, but also because they offer a different level of accessibility and potential for collaboration over traditional offline software. However, it became evident that as these are commercially developed tools that prioritize specific functions, they lack the adaptability to meet URA's broader planning responsibilities. These insights solidified our conviction to develop a custom web tool tailored to the specific needs of urban planning and design within URA's context. In the following section, we'll outline the methodology that guided the design and development of the web tool. Firstly, the tool's design workflow was centered around these 3 main tasks. In site subdivision, users begin by drawing a site boundary and specifying 2 access points. They can also input a few additional algorithm-specific parameters. Based on these inputs, the tool will then automatically generate a range of subdivided layout options, allowing users to review and select one to proceed with. In building generation, users simply select the parcel that they want to generate building layouts on and define the range of parameters that they would like to explore. our tool then runs an optimization process and presents all of the explored layout solutions in the following tasks. And in this third task, solution exploration, users can quickly compare generated results using a carousel widget to toggle between the options. Each solution is not only visualized in 3D, but we also visualize them and position them on a scatter plot, which is here, highlighting its performance relative to the other solutions that has been explored during the process. The workflow that link these three tasks together are built to allow an iterative process. What an iterative process means is that after the end of each task, users are allowed to repeat the process with the new insights that they gain from completing the task. This iterative process between tasks represents a departure from the traditional linear workflow typically associated with models that are built in Grasshopper. When we are designing the generative models used for the first two tasks, we prioritize parameters that reflected planners' typical concerns over geometry-based parameters. This includes parameters such as site coverage and block key types for the building generation model, and also site access points for the site subdivision model. Our tool is a full stack system that integrates a React browser interface that's aligned with ePlanner. And number two, a Python backend that handles the geometry optimization and data analytics part of the computation. And number three, an external Rhino compute server to utilize Grasshopper's vast existing capabilities if needed. And number four, a serializable JSON data structure that links all four of these modules together. The considerations that went to the design of this data structure was crucial to ensure the interoperability between the tasks and transparency for sharing results in the future. This idea is further expanded upon in Chapter 6. Before designing the user interface, we conducted an intermediate study with students first to gather some preliminary insights and better inform our final decisions for the user interface. The final interface has three main parts to it. Occupying the largest space in the center is a 3D viewer that provides visual feedback and also acts as an interface for users to interact with the geometries. On the two sides are customizable side panels that we developed to expose parameters and also additional information to the users based on where they are in the design workflow. Finally, at the top, we display a live metric. Our preliminary workshop revealed that not all metrics are equally important to the planner. High-level targets such as number of dwelling units align with national-level agendas, and these take precedence over performance metrics that can be refined later on in the process. Hence, we chose to keep this metric exposed in the tool. To evaluate this tool, we conducted a workshop with 32 participants from URA from various departments. During the workshop, participants used the web tool over an hour to identify the number of dwelling units in this given site. We collected the data based on how the users navigate the tool by implementing click tracking, and we also conducted a survey at the end of the workshop. The results from the survey show that users report a high level of satisfaction, an above average Likert score of 4.0, and this citing the tool's ease of use and the speed of inputting parameters for each step, comparing results quickly using the Trade-off Explorer, and generating results for first cut options. On the other hand, some users were dissatisfied with the simplified support materials, preferring more technical details. They also wanted not just the ability to iterate the process, but also the ability for adaptive design refinement, an important concept that we will revisit in Chapter 6. When analyzing the user journeys, we first visualize all the journeys as a standard structured graph. This graph shows us a clear map of the tool's design workflow and showed how most users followed the intended workflow as well. However, this falls short in capturing the iterative process feature of our tool, which prompted us to explore alternative methods to visualize user journey. After some research into user journey methods, we found that representing the data as an unrolled acyclic graph, or UAG, can effectively capture the iterative process. This method allowed us to capture the branching and nonlinear nature of the user interactions. We repeated the analysis of the user journey with UAG, and we have also mapped each of the user journey with their profile gathered from the survey. From this cross comparison, we can analyze for different user types based on how they interacted with the tool. And more importantly, this study showed me the potential of using UAG as a means of visualizing design exploration. In the next chapter, chapter 4, we asked, given that the challenges of using many model types, parameters, and objectives, what computational intervention can support a more efficient and user-friendly design optimization? We modified NSGA3, which is a optimization algorithm, with DBSCAN, which is a clustering algorithm, to automatically focus the search on more promising regions of the design space without the need for user-defined parameter boundaries. This study is also published in CAD Futures of 2023 conference. In this study, we chose to further investigate genetic algorithms, or GA, as our foundational optimization solver. Based on our findings from the literature review, we showed that 50% of the 57 articles that studied optimization in the context of urban design, they employed some form of GA. And despite common criticisms about GA's relatively lower performance compared to other optimization methods, this widespread adoption highlights its continued relevance and practical appeal. During the setup of a standard GA, users must first set the upper and lower parameter bounds for the optimization algorithm to explore within. Many users often do so without fully understanding the model, making this user-decided limits somewhat arbitrary. Our method lifts this burden from the user, and we start by starting with the global min and max boundaries instead of the user-defined ones, and then guiding the crossover and mutation step in the GA to concentrate only on promising design spaces. This proposed method divides the GA into two phases separated by an intermediate termination point. At this point, a subprocess is triggered. This first step of the subprocess is then to identify the top performing solutions based on the fitness percentile parameter. The second step identifies the promising design spaces based on the parameters used by the top performing class solutions. DBSCAN is used to find these clusters that are shown in gray. The sensitivity of this clustering is controlled by the second parameter, epsilon distance. And the third step is then to modify the crossover and mutation operation to only allow future exploration to happen within these identified design spaces. At this stage, the GA then resumes and continues until the final termination criteria is reached. We applied this method using two sequential tasks. The function of these two tasks are similar to the tasks that I just presented in chapter 3, but the parameters and objectives used are different. Combined, they form an integrated model with 7 parameters and objectives, and 7 objectives to optimize for. To evaluate the performance, we conducted 4 optimization runs with a standardized computational budget across all 4 experiments. The first run uses a standard NSGA3 to act as a baseline, while the next 3 experiments implemented our method with varied parameter settings. The effect of these varied parameter settings can be seen in the figure on the left, where experiment 2, this one, formed fewer but broader clusters. Experiment 3 is formed more but narrow clusters, and experiment 1 balanced both of them. Experiments 1 and 3 with narrower search spaces converge faster. And it also found the top performing solutions from the combined comparison. Their less skewed performance distribution also indicate above average outcomes, highlighting the value of focused search. These results validated the approach, and in the future, the algorithm can also be integrated into a web tool. I envision embedding the algorithm as a widget in the web tool to enhance usability by recommending design spaces for the user. Optimization can be conducted in the background to pre-compute these promising design spaces as the users continue to use the tool. The resulting recommended design space can then be shown to the user as a color map overlaid over the parameter sliders. And this can guide the users visually without strictly restricting their exploration. In chapter 5, we asked, given that long simulations create a computational bottleneck in the optimization process, what computational intervention can help accelerate optimization? In this study, we propose a set of morphological feature extraction methods to train circuit models for approximating annual energy use intensity of residential buildings, specifically in Singapore. The model accelerates optimization without the need for retraining models to explore new morphology. And this work has been published just this year in the Journal of Building Performance Simulation. We begin by reviewing studies that directly address generalizability in surrogate models for the built environment. Firstly, surrogate models, they are simply regression models that are trained to approximate expensive computational simulations that architects and planners are all aware of, such as CFD and energy modeling. A surrogate model that is generalizable means that it can be applied across a wide range of parameter combination. We found that while various studies have claimed that their surrogate models are generalizable for facade, building system properties, and climate, we found that generalizability for morphology, morphological features are often oversimplified, with most studies relying on basic geometric descriptions such as depth, width, and height. Using annual energy use intensity, or ANOEUI, as the main performance indicator to train our surrogate model on, we then investigated morphological features that are commonly explored in the context of urban planning and design and compared their impact to ANOEUI. This includes the shape, orientation, and height of the building, but it also includes the distance and height of surrounding buildings. The results show that all of the features studied impact ANOEUI of buildings to some extent, with the footprint shapes having the largest impact. We then propose the use of 3 methods to extract those features that I just explained. To quantify footprint shape, the Mahatos library in Python was used to extract the Zernike image moments from a binary image of the building footprint. To compute the rough orientation of the building, principal component analysis is used to calculate the building's major axis, which is then used to calculate the angle to true north. And finally, to analyze its surrounding context, ray casting was used. A set of rays are projected radially outwards and captures the distance and height of the first building that each ray intersected with. Using these morphological features, we can then train the surrogate model to be generalizable across not just any building shape, but also in any built context. The dataset for this study comprises of over 9,000 residential buildings in Singapore. This data is sourced from OpenStreetMap and enriched with building height by matching each of the building with the gross plot ratio, or GPR, of its corresponding land parcel, which is taken from Singapore's 2019 master plans. From this, we randomly sampled 4,000 buildings, as shown as red dots in the scatter plot. Our sampled data ranges from small buildings in very dense neighborhoods all the way to tall buildings in sparse neighborhoods. An example of the data included in 1 and 3 can be seen here, as the building in red is the building that we wish to approximate the ANOEUI for, and the context is shown in wireframe. This flowchart shows a simple parametric workflow used to convert the raw data into thermal zones for simulation using EnergyPlus. As the focus of this study is on morphological features, we use standardized parameters for facade, building system properties, and weather. To improve the accuracy of the surrogate model, we conducted a hyperparameter optimization process, varying not just the features, but the type of regression model used and its associated hyperparameters. We split the 4,000 samples into testing and validation set using an 80:20 ratio. The process resulted in 4,000 surrogate models trained. To evaluate these models, we use root mean square percentage error, or RMSPE, and maximum absolute percentage error, or max APE, as measures of average performance and also the worst case error, respectively. We compared the result surrogate models in a few manner. To achieve the lowest max APE, we found that gradient boosting performed the best amongst all the regression models. Using Zernike image moments between the 5th and the 9th order, and also moderate ray counts here for the polar ray casting, it also led to better results on average. Finally, including all 6 feature sets, produce accurate models result on overfitting. To identify the most suitable surrogate models out of these 4,000, we conducted an analysis to find the Pareto set of models, which are labeled A to F. Each of these models represents equally good solutions with small trade-offs between the 2 metrics. However, if I have to choose one single model, our priority is to minimize large prediction errors, and so our recommendation would then be solution F. To conclude, I would like to propose a way to integrate this surrogate model in an urban setting. This can be done by applying the model repeatedly to predict annual EUI of many buildings at an urban scale. When used for exploring many building layouts, this method would significantly reduce computational costs. And finally, in chapter 6, we ask, how can we prototype a modular, adaptable, and transparent optimization framework that addresses the structural and computational challenge of urban planning and design, and validate it through real-world case studies and collaboration with planning practitioners. In this study, we proposed an optimization framework that decomposes urban planning processes into modular dependent subproblems. We then developed a unified JSON-based data structure to ensure transparency and also interoperability. Our framework then is then designed to enable heuristic search for adaptive design refinement of urban design solutions. If you wish to try the computational framework from this study, feel free to clone it from our Net Zero Sutures Lab GitHub. This study incorporates the following outcomes from the previous study. From chapter 3, we expanded the initial formulation of tasks and data structure. From chapter 4, we reused the algorithm for building generation. And from chapter 5, we reused the proposed surrogate model. From my review of optimization frameworks, 2 frameworks stood out from the rest. First is the meta-parametric framework by Abraham and our own Professor Sam Joyce on the left. This framework automatically creates new parametric models by modifying the topology of the original given parametric model. The cognitive computing framework on the right by Professor Reinhard Koenig introduces the idea of a container of evaluation models, which allows the system to evaluate a solution across a broader set of objectives. These 2 frameworks essentially addresses the limitation of exploring just a single parametric model by expanding the design space and also the solution space respectively. Doing so potentially uncovers more optimal solutions that might have remained unexplored if we were only using the original parametric model. With these 2 frameworks as the basis, I further developed these ideas into the framework that I will present by orienting it specifically for the challenges of urban planning and design. To do that, I'm proposing to define urban planning and design as a multi-component problem. Multi-component problems are problem definitions that can be broken down to independent tasks. Implementing this idea to solve would require a shift from the use of single monolithic integrated models to a multi-component framework of many tasks, models, and features. To begin the methodology, I would first like to define the terms that I just used. Features represent a spatial object that's associated with properties. This definition mirrors the definition of features as used in GeoJSON. GeoJSON is an open standard for encoding geographic data. This study implemented 3 commonly used features in many planning studies, namely parcel boundaries, road center lines, and building footprints. The unique feature that we added to this study is the study area. This is defined as a polygon that delineates the boundary within which features can be modified. Features outside of this study area cannot be physically changed by our framework, but are still included when evaluating the quality of the overall urban design. The function of study area mirrors how planners would typically approach brownfield redevelopment scenarios, and it plays a key role to our implementation of adaptive design iterations. Tasks are then processes that take one or more of the features as inputs and transform them into new or modified features. In this study, we implemented 4 tasks. The first task is change study area, refines the study area feature. The second task, site subdivision, subdivides the study area into smaller parcel boundaries. The third task, land use density allocation, assigns land use and GPR to each parcel. This study, however, limits the land use to residential type only. The fourth task, building generation, generates building footprints within each parcel boundary. This figure shows the dependency of the task implemented. It is generally a linear workflow with the exception of the task land use density allocation that must be completed before the task of building generation. Each task is associated with a container of models. In this study, we implemented one generative model for the task of change study area and land use density allocation, and 2 models for site subdivision and building generation. In order to demonstrate later on in the results section, the framework's capability of adaptively using different models during design refinement. In our framework, we also explicitly distinguish between generative models and evaluation models. Generative models are models that create features or create new features and properties. Evaluation models are then models that assign metrics as properties to existing features. This distinction enables users of the framework to be selective and rigorous when choosing evaluation models, but still allow for flexibility when experimenting with different generative models. To give a more intuitive and visual explanation, this figure shows the intermediate states of the urban design solution after a model from each task has been applied to it. After the change study area, all the features within the selected orange study area would disappear. And then after site subdivision, each of the orange study area is subdivided into parcel boundaries. And after land use density allocation, we allocate GPR all of these parcel boundaries. And finally, after building generation, we put in the building layouts for each of the parcel boundaries. Iteration 1-4 hence represent a complete urban design solution that has undergone all the tasks that we implemented. At this stage, we can then repeat this process, moving to iteration 2-1 and focusing on a different area of the urban design solution. This highlights the adaptive design refinement capability that I was talking about earlier. My definition of an adaptive design refinement is the process of reapplying the computational models to iterative design outcomes by shifting focus across different areas of the urban design solution. It's not just about tweaking parameters using the same model to get different results. The figure shows the adaptive design refinement of an urban design solution that has been iterated over 3 cycles with shifting focus and also applying different models to it. And this embodies the principle of adaptive in the adaptive design refinement. By having multiple models for the same task, we allow the framework to test itself by comparing outcomes from different generative approaches. This is in direct response to another key insight that we received from our conversation with the planners, where we found that if by using different models during optimization, it would improve the user's confidence that the final proposed results are truly optimal. In a separate study, out of the necessity to build all these generative models to test our framework's capability, I explored the use of AI for the creation of these generative models. Since this computational framework is also structured as a repository, with today's technology, it's easy to get ChatGPT to create these generative models with new design logics while adhering to our standards for inputs and outputs. The figure shows outputs from 7 building generation models developed using ChatGPT. I did not include these models as part of the study because the results are not yet robust. However, it offers a promising glimpse into how AI could assist in automating the creation of generative models in the future. Next, on evaluation models, this figure illustrates the 4 evaluation models that are implemented in the studies, which are NOEUI and view obstructions for the feature of building footprints, GPL deviation to evaluate the feature of parcel boundaries, and density reach to evaluate the feature of road center line. The technical definitions of each model can be found in the dissertation. This figure shows the data structure that we designed, and it represents a complete urban design solution shown here. First and foremost, the data is designed as a JSON file to ensure serializability. In other words, human-readable data format. At the top, we see the evaluation section, which stores the aggregated metrics from all of the conducted evaluation. Next, we have the metadata section, which stores information about the solution's design lineage. This includes a simple unique ID, which is a chain of 5-character hex codes that is appended each time a new generative model is applied to it. We also keep a list of the parameters used by each model. With this metadata, we can easily find task solutions that were iterated upon to arrive at this selected solution. Finally, at the bottom, we store all the features that are included in this specific urban design solution. With the added capability of adaptive design refinement, we needed a new form of visualization to capture this idea of design lineage that I just mentioned. To do this, I modified the UAG method as used in Chapter 3 to visualize different trajectories of exploration. The difference is that the user journey in Chapter 3 was collected from a real user, and the user journey that you see now is generated from an automated heuristic search. In this method, graphs can have non-uniform branches, depths, and widths. Each new node represents a complete urban design solution that have undergone all of the tasks that were implemented. To add on to that method, by coloring each node with the combined score of the aggregated metrics, the graph can then effectively convey the performance of all the explored urban design solution at the same time. This figure shows a snapshot of the exploration trajectory map at different number of iterations. To create this figure, beam search is used as an heuristic search strategy. However, it's not the only strategy that can be used with our framework. To demonstrate that, we explored a total of 4 different heuristic search strategies. These strategies differ along 2 key dimensions, whether they are sampling-based or optimization-based, and whether they conduct deep or shallow search. These deep search strategies support the adaptive design refinement capabilities, whereas shallow search cannot. These 4 strategies are explored over 6 experiments. Each experiment is given the same computational budget of creating 5,000 total urban design solutions. Experiments 1 and 2 explored random search and reference search respectively. Experiments 3 and 4 investigated the genetic algorithm using different values of population size. Experiments 5 and 6 investigates beam search using different values of branching factors. Firstly, visualization of the results from experiment 6 highlights how deep heuristic search enabled variation in the morphology of the solution, even though they came from the same baseline solution. While a greater number of iterations does not always guarantee better performance, these iterations that have undergone many cycles of adaptive design refinement tend to exhibit very diverse morphology as a mixture of models have been applied to it over many cycles. This figure then compares the performance of all the solutions across the 6 experiments. This comparison highlights 3 key findings. Firstly, optimization clearly outperforms sampling. Experiments 1 and 2, which use the sampling heuristics, failed to produce any of the top 20% of solution. Second, model choice methods. Experiments 3 and 4 shows the outcomes are highly sensitive to the generative model used. Each of the quadrants from these two experiments were conducted using different combination of models. The right model combination, for example, here and here, led to significantly better results, while weaker combinations consistently underperformed. And thirdly, iteration would improve performance. In experiment 5, we can see that the high-performing solution emerged through multiple refinements from an initially average baseline design. To conclude, this chapter proposes a multi-component optimization framework for urban planning and design. The realization of this as a fully working computational framework is the result of 3 core ideas and also contributions from previous studies. First, we propose the idea of modularizing tasks within urban planning and design, whereby the act of selecting the task for any urban planning design project upfront will clear up any ambiguity in the scope and the hierarchy of tasks in that specific project. Each of these tasks are then associated with a container of models so that planners are not tied down to one way of doing things. The framework the framework would work even if more tasks and models are added in the future. This is possible because of the second key idea, which is that the formatted data structure. Following the JSON-based data structure would make it completely transparent and also extensible. And finally, these two ideas make the third core idea a reality, which is the capability for adaptive design refinement. This added capability distinguishes this design workflow of my computational framework from most other tools. Bringing this framework back into the practical context and informed by the insights I gathered through my interactions with URA, this final figure illustrates my proposed approach for implementing the framework within a realistic working environment that involves dynamic collaboration between different working professionals. To conclude, I would like to revisit some of the research questions that was put forth in the beginning. To answer RQ1, we conducted a literature review to identify the specific gaps. To answer RQ 1.1, I developed a customized full-stack framework to support semi-automated iterative workflow as a plugin for ePlanner. This study is validated through many extensive workshops with planners and students alike. To answer RQ 1.2, I proposed integration between NSGA3 and DBScan to search in discontinuous but rewarding parameter spaces. And this improved the convergence rate, found better solutions while removing a technical barrier that was faced by users. To answer RQ 1.3, I accelerated the optimization process by using instant approximations with the surrogate model. The training of this model utilized new features that prioritize morphology. And this methodology is also applicable for training surrogate models for other metrics as well. And finally, to answer RQ2, I formalized urban planning and design as a multi-component problem structured around user-defined interdependent tasks. I designed the framework to be task and model agnostic to adapt to future problems and methods. I developed a serializable data structure to support transparency, interoperability, and also traceability of the design solutions. I enabled the search of the use of different search heuristics that allows for this capability of adaptive design refinement. And all of this, to study all of this, I incorporated key methods and practical insights from prior studies at workshops. This thesis acknowledges some limitations and proposes them as future directions. From chapter 4, it'll be good to validate the usefulness of the proposed UI in a practical context. From chapter 5, I would like to work more on creating new generalizable surrogate models for other important metrics that's useful for urban planning. And from chapter 6, it'd be good to integrate more tasks and features into the framework to test the robustness of this framework that I'm proposing, and to incorporate elevation to the data structure as well. This slide shows publications that have resulted from my research throughout the PhD. And before I end, I'd like to share a few final words. I recognize that optimization, modeling, and design exploration are each specialized domains, and urban planning and design is already a broad and multifaceted field. To address these challenges, I had to work across multiple problem areas while learning enough about each to make a meaningful contribution. This is what was necessary in order to design this framework that not only targets the root of the problem, but also remains practical to implement. The work presented in this thesis, together with its proposed future development, will likely require continued coordination between practice and research. The framework presented in this thesis offers a way to begin building towards that future today. And assisted by the right adaptive optimization framework, I believe that the field of urban planning and design can increasingly rely on simulation-driven evidence to inform decisions amid growing complexity. Thank you for listening.